Turkey, Haiti, Indonesia, Japan, New Zealand, Chile, California, even New York City and Washington, D.C. These are just a few places in the world that have recently been hit by an earthquake or tsunami. Earthquakes and tsunamis have been occurring since the dawn of time, and they will continue as long as the Earth rotates around the Sun. Humans may never be able to prevent them, but we can definitely prepare to survive them better. One organization is dedicated to limiting the enormous amount of physical destruction, economic disruption, and human carnage that they leave in their aftermath. The George E. Brown Jr. Network for Earthquake Engineering Simulation, or NEES, is pioneering the mission to reduce the impact of earthquakes and tsunamis on society through research, engineering, science, and education.
Known for its cutting-edge research at the laboratories, NEES is also helping the earthquake engineering community to become more collaborative and interconnected, not only in the United States, but globally.
Earthquakes are the result of a sudden release of energy in the Earth's crust that creates seismic waves. They are caused by the rupture of geological faults. A tsunami can be generated by underwater volcanoes, an underwater landslide, or when an earthquake abruptly deforms the sea floor and vertically displaces the water above it. Both earthquakes and tsunamis can cause a tremendous amount of damage to infrastructures. Buildings can collapse. Foundations can crack. Roads, bridges, pipes, and other infrastructure can also be destroyed or compromised, not to mention the displacement of people from their homes and cities. NEES is dedicated to providing engineers, architects, and other practitioners with the critical research they need to design structures to perform well during earthquakes.
By coordinating the experimental research in earthquake engineering at different labs in the United States, we get information that we otherwise don't have. This type of information is necessary for us when we try to design new and modern structures.
NEES facilitates research at 14 testing locations in conjunction with various major universities across the nation, with headquarters of operations at Purdue University. The facilities are equipped with major research assets that vary from an enormous tsunami wave basin to a shake table that simulates the ground motion during an earthquake and can put a bridge support, a full-scale building, or even a wind turbine through performance tests. The results indicate improvements that can be made to building codes and construction techniques so that the infrastructures we rely on can undergo an earthquake or tsunami and remain functional. This research is then shared with engineers, researchers, and practitioners around the world through the NEES Hub. The NEES Hub applies Hub Zero technology, which is a new way for scientists and engineers to publish and share information. Researchers are able to run models using a simple internet interface that will connect to the supercomputing resources on the NSF's XSEED and the National Open Science Grid OSG. This allows for quick processing of simulation. The NEES Hub brings world-class research to any place in the world that has broadband internet access.
All of this combination of experimental facilities as well as cyber infrastructure makes NEES an invaluable national resource, which has the single purpose of accelerating improvements in seismic design and performance by serving as a laboratory without walls for researchers, educators.
Finding the projects on the NEES Hub is pretty easy, and you can find it and also several data that they have from different tests. You can have that and you can download that and you can use in your analysis. So there is no need to chase the data.
Another important component in the NEES mission is education and outreach. It implements programs to engage our youth, students, practitioners, and even the general public. Currently, many experiments funded by the National Science Foundation, other federal agencies, and industries in NEES are being conducted by researchers from the U.S. and abroad, showing the impact of earthquakes and how to minimize the damage. One experiment recently showed how the traditional orthogonal design of placing shear studs allows slab cracking in concrete and could lead to premature failure. Research showed that by using a radial layout of the studs, the concrete could withstand far more shaking without cracking, and because of this, building codes are being changed to reflect those results.
There are many formulas in the building code. Some of them are decades old. Some of them are a few years old. Many of them are based on analytical research. Some of them are based on experimental research. When we try to do something new, those formulas might not necessarily apply. We need experimentations such as the ones that NEES coordinates in order to see if the formulas that we are using are applicable to the new situation or not.
At the NEES Tsunami Wave Basin at Oregon State University, they are simulating landslide-generated tsunamis and accurately measuring the characteristics of the landslide and the waves. At the facility at the University of California in San Diego, they have tested a full-scale reinforced masonry shear wall structure that you might find in a typical apartment, school, or hotel. This experiment on the world's largest shake table subjected the structure to a magnitude 7.5 earthquake. In Los Angeles, researchers from UCLA placed sensors throughout the landmark Los Angeles Airport theme building after it was retrofit to withstand the big one. Using a portable mass shaker called the Mighty Mouse Shaker, they excited the building and confirmed the retrofit design and analysis assumptions. Building earthquake and tsunami-ready structures requires an enormous amount of testing, research, simulation, and experimentation. By proactively creating and simulating the stress, shaking, and deformation inflicted on a structure during these natural disasters, we can construct an infrastructure that will remain standing and functional when the big one hits.
We envision NEES becoming an active and engaged collaboratory where researchers and educators share new knowledge, contribute data and tools, provide new design techniques, and most important of all, through the educational activities of NEES, we help educate the next generation of earthquake engineers and researchers, the leaders of tomorrow.
Every day, NEES continues to accelerate improvements in seismic design and performance by serving as an indispensable collaboratory for discovery and innovation. The pioneers at the Network for Earthquake Engineering Simulation are helping to make it possible for our structures to stand up to earthquakes and tsunamis, and this can help prevent these natural disasters from becoming heartbreaking tragedies. For more information about the George E. Brown Jr. Network for Earthquake Engineering Simulation, log on to nees.org.
One year after a massive tsunami killed thousands in Japan and threatened the Oregon and Southwest Washington coasts, scientists are still getting some valuable information from the disaster.
Oregon scientists are even creating their own tsunamis to learn even more now. And K2's Lincoln Graves shows us a one-of-a-kind facility at Oregon State University that helps people understand these killer waves.
Everything's controlled from up there.
Down on the floor, William McDougall waits patiently.
His colleague, Melora Park, gets things ready inside the control room.
I have to start with the boards in the 0 positions.
William gets the go-ahead, eager to show us his experiment.
Are you ready? Okay, we're ready.
Okay, we're starting the wave maker.
It's the tsunami wave pool at Oregon State University, and it gives an up-close lesson on how tsunamis behave.
Oh, this is totally cool stuff.
The current setup shows what happens when a tsunami runs into an ocean breakwater or harbor, which this yellow barrier represents.
This whirlpool or vortex spun off the end of the breakwater from Japan. The videos of the ships and vessels caught in a whirlpool is exactly this.
The size of those whirlpools took some scientists by surprise. They designed this experiment in response to study how the whirlpools move and how long they last. Even these small vortexes took time to settle down.
These are very persistent, so once you spin them up, they may last 5 minutes here, but they may last 10 times that long in reality.
And that's just one experiment. The pool can generate all kinds of waves and can be reconfigured for any scenario. Researchers constructed this scaled-down model of the town of Seaside a few years ago and ran several waves into it. The result was eye-opening. Experiments like this show scientists what could really happen in a natural disaster, rather than just imagining it. Why scientists here call this pool a valuable research tool.
Hopefully, maybe eventually save more lives is, what we're trying to get to.
Lincoln Graves, K2 News.
Boy, that is really eye-opening. OSU Tsunami Wave Pool receives very little state funding.
In fact, most of the research there is done with private dollars, such as research grants and donations.
NEES at Berkeley is an equipment site of the Network for Earthquake Engineering Simulation. And similar to the other sites, it started in year 2000. Until 2004, this was the construction period. And then from 2004 until now, it's in operation. So the research in the labs typically strive for these innovations in design against earthquakes, or retrofitting for existing infrastructure, or completely eliminating the effect of earthquakes, such as using isolation or advanced material. In NEES at Berkeley, we have what I call 3 frameworks. The first one is for physical testing, where people build specimens, attach it to our strong floor, and have actuators that are reacting against our reaction zone. The second framework is an interface framework between the physical experimentation and computational simulations. The third framework is the pure simulation framework, which is OpenSeas. So the combination of these 3 frameworks, the physical framework, the interface framework, and the simulation framework, is what makes NEES at Berkeley really unique.
This is NEES at Berkeley, one of the experimental sites of NEES network. Main features of the lab is strong floor and reconfigurable reaction wall. Reconfigurable reaction wall is It's very interesting concept because in this case you are not stuck to certain configuration, to certain geometry of your wall. In this case, if your setup requires a certain configuration of the reaction wall, you can disassemble the wall. Right now we have 3 towers connected to each other. You can disconnect those blocks and put those blocks anywhere on the floor, press them, and create a new wall anywhere on the floor. In addition to that, we have the biggest press in the United States, which is behind of me. So we can provide 4 million pounds in compression, 3 million pounds in tension. Then we have high-performance actuators. We have 4 high-performance actuators and 3 static actuators. Then in addition to that, we have a data acquisition system which can provide 196 channels. We have 2 controllers. One of them is capable to control 8 actuators, the other one is capable to control 4 actuators. The lab promotes and develops a hybrid simulation technique which is focusing on testing large-scale structures by combining fine filament analysis technique and testing. So in this case, if you have a multi-story building, you can model part of the structure in a computer and the rest of the structure can be tested on the floor. And this communication between your model and the test article on the floor can be done in real time, can simulate a response of that building during real estate.
We conduct a wide variety of outreach activities here at the NEES at Berkeley Laboratory at UC Berkeley. One of the popular ones that we conduct for researchers is a hybrid simulation workshop. We host that about once a year, and we have researchers come out from universities across the United States, as well as a few participants from abroad, and they come to learn about the hybrid simulation capabilities here at the laboratory. As a result of this workshop, many of them go on to write NEES-R research proposals and eventually, hopefully, get funded to come back here and do their research projects here at the NEES at Berkeley Lab. Our other kind of highly dynamic and exciting program that we have in our outreach arsenal here at UC Berkeley is our K-12 outreach program. Through this program, we leave the students with a set of Kinects, building materials, from which they are able to break up into teams and design and construct their very own earthquake-resistant structures. With those Kinect buildings, they're able to bring them out to our laboratory on a follow-up visit as a field trip here to the labs and test them on our earthquake simulator. During their field trip here, we also get to have them participate in a laboratory tour where we show them some of the equipment we use, and for many of them it's their first time actually being in a research environment. In the 2010-2011 school year, we worked with 47 different classrooms, mostly in the Oakland Unified School District, and really gives these children the opportunity to come out to our laboratories and see what it's like to do research and what real science is all about.
Chile was shaken by a magnitude 6.7 earthquake last night. It was one of 13 powerful quakes around the world so far this month. Today, Ben Tracy witnessed a man-made earthquake in San Diego. It was part of an experiment to prepare for the real thing.
3, 2, 1.
It's hard to tell, but this 5-story building is experiencing an 8.8 earthquake, moving just inches in each direction. Inside, things barely moved during today's simulations, thanks to these giant shock absorbers which protected the building from most of the shaking. It was an unprecedented test of so-called base isolators. Jose Restrepo is an engineer at the University of California, San Diego.
The ground is moving a lot and the building is staying put. It's like it's been hanged from the air for a while the earthquake moves.
Similar seismic improvements are being made on the Bay Bridge in San Francisco. This animation shows how the bridge should be able to absorb the shock of a major quake.
This is utterly unique. It has not been done.
Mike Gardner heads the California Seismic Safety Commission and says today's building test was one of the most realistic ever done.
We have lots of data on buildings that have been shaken in real earthquakes and how they have failed, but we have not been able to measure during the course of the shaking what happens to the building, and that's a real key.
The point of this test is to see how engineers can improve buildings such as hospitals and schools to keep them functional after a major quake hits. So while this may not look like much from the outside, inside it's very realistic.
There is a mock operating room and intensive care, heating and cooling systems, and even elevators. The building sits on top of powerful hydraulics that can simulate nearly any earthquake.
1994 Northridge earthquake.
One test simulated the 6.7 magnitude quake that hit Northridge, California in 1994.
We're having an aftershock right now, people.
57 people died and the quake caused $20 billion in damage. Since then, thousands of structures in California have been retrofitted to withstand even stronger quakes.
And researchers here in San Diego have plans for more tests next week. They're actually going to take those shock absorbers out from underneath the building and see what kind of difference it makes. And Scott, they're telling us they expect a lot more damage.
Fascinating, Ben. Thanks very much.